Good morning. In the last classes, we discussed Module 1 and Module 2. In Module 1, you studied P-N junction diode, P type of materials, semiconductor materials, N type of semiconductor materials, application of diodes, operation of the diodes, rectifiers, regulators with filters, etc. So those are the topics you studied in first module. In the second module, you studied MOSFETs, JFET, FETs, enhancement MOSFET, depletion MOSFET, N channel JFET, P channel JFET. Those are the topics you studied in module 2, and also you studied SCRs, 2 transistor logic SCR, etc. The next module is operational amplifiers and its application. Call this as operational amplifier. Why we are calling this as operational amplifiers? Not only the amplifiers, because we know that the amplifier is nothing but a circuit which increases the strength of the signal, That is nothing but the amplifier. The operational amplifier means, in addition to the amplification, it also performs the different mathematical operation such as addition, subtraction, integration, differentiation, etc. So those are the operations are performed by this type of circuits, hence the name operational amplifiers. Its application, I told that just now, operational amplifiers, adder, subtractor, differentiator, integrator, inverting, non-inverting. So those are the applications of this operational amplifiers. So we can use this for comparison also. We can call this as comparator. So the operational amplifiers are also called as OPAMPs. That OPAMPs can be used as an comparator. Okay. So these are the topics which are present in the module number 3. We discuss in detail. So before going to that, we'll consider how many inputs are there, how many outputs are there. We'll discuss that. The symbol of OPAMP is represented by like this. So this is the symbol of operational amplifiers. It consists of 2 inputs and it has only one output. And to operate any electronic device, we require an voltage supply. So that is positive voltage VCC and negative voltage VEE. So this is about 12 volts to 15 volts. This is about minus 12 to minus 15 volts. That is the voltage we are applying for the operation of the OPAMPs. VCC is 12 volts or 15 volts. So this is negative voltage, which is minus 12 to minus 15 volts. It has 2 inputs, 2 input terminals are, this is negative terminal and this is positive terminal. And this negative terminal is called as inverting input, terminal or inverting input, and this positive terminal, this positive input is called as non-inverting input. So these are the 2 inputs, and the OPAMP has only one output, that is the output pin, and 2 supply pins. So this the symbol or block of the OPAMPs or operational amplifiers. This is also called as differential amplifier. That means for the inputs, we are applying inputs are V1 and V2. Assume that this is V1 and this is V2. The output is represented by VO. The inverting input is V1, non-inverting input is V2. The difference of these two is amplified by the OPAMP and gives the output. Let us consider that for all the amplifiers which has its own gain, amplification factor. The amplification factor that is represented by A. If it is voltage, that is represented by AV. If it is current, that is represented by AI. Depends upon the input. So if the current is the input, we are considering gain of the OPAMP as AI. If it is voltage, then we are considering that as a AV, that is voltage gain. Therefore, the output is the difference of these two with amplification factor, that is VO equal to AV into V2 minus V1, because we are applying the input V2 at the positive terminal and V1 at the negative terminal. Therefore, the difference of these two into the gain parameter, amplification gain factor, amplification factor, that is nothing but the AV V2 minus V1. This OPAMP, operational amplifier, is also called as the differential amplifiers because it is amplifying the difference of the two inputs. Some parameters. For example, consider the first parameter is virtual ground property. Virtual ground means, let us consider that these are the two inputs, that is V1, V2. Now, if this terminal is grounded, is connected to common ground, the voltage at V2 is equal to 0 because this is connected directly to the V2 is connected to the ground, that is 0 potential. Therefore, V2 at this terminal, the voltage is 0. So that means due to virtual ground property of the OPAMP, whatever the voltage at this point, same voltage is present here also. That means V1 is also a 0. Virtually it is connected to a ground. Therefore, this property is called as the virtual ground property. But V1 is not connected directly to the ground, but V2 is connected to the ground. So due to this, this V1 is also acts as a ground potential. This concept is called as the virtual ground concept. Let us consider that the next one, V2. V2 is equal to 3 volts. Let us consider that this is 3 volts. Therefore, due to the virtual ground property, whatever the potential at this point is same as the potential at this point. Therefore, V2 equal to V1, that is equal to 3 volts. This voltage is equal to this voltage, and that is whatever the voltage at this point is present at this point. That is nothing but the virtual ground property. We will consider some characteristics of the OPAMPs. In first one, input resistance is infinity. We are considering ideal characteristics. We can call this as ideal characteristics of OPAMP. Now here the input resistance is infinity. That means the input resistance of the OPAMP is very high, that is infinity in ideal cases. The resistance is infinity means the current is almost 0. That is the property number 1. If it is practical case means input resistance is about mega ohms. The second characteristic is 0 output resistance. The the OPAMP has 0 output resistance. This can drive many circuits. The output resistance is 0. For the practical case, it is about 5 ohms. Third one is bandwidth. OPAMP, operational amplifier. It is amplifying the signal. In this, the bandwidth is infinity means this OPAMP can amplify any signal of any frequency. This OPAMP can amplify the signal with any frequency. That's why we are calling the bandwidth is infinity. Next one, common mode rejection ratio is infinity. The noise, we can call that as noise, unwanted signal which is present during operation value. We have to eliminate or suppress the noise value. The common mode rejection ratio is very high. It will remove all the noises. That is the meaning of the common mode rejection ratio. So these are the characteristics of the ideal op-amp and also practical op-amps. Next, we will consider two types of op-amps here. One is open loop, closed loop op-amps. Okay, open loop and closed loop op-amps. Consider first one is open loop. Here in open loop there is no control between the output and the input. The output is independent of the input. Whatever the input, so you will get the output. So there is no control. That is nothing but the open loop configuration. If this is the case, the open loop gain of the system, output voltage gain is nothing but infinity into input voltage, Vi. I will call this as input voltage. These are the two input voltages. In open loop characteristics operation, the output gain, voltage gain is infinity. If it is infinity means, if you apply the 1 volt of input, so into infinity, the output is nothing but what? So infinity into 1 volts, then what happens? So you will get infinite voltage. In order to avoid this, we are going for the closed loop configuration. If it is infinity means, if you apply the 1 volt of input, so into infinity, the output is nothing but what? So infinity into 1 volts, then what happens? So you will get infinite voltage. If you go for 2 volts of input, so 2 infinity, that means very large value. That means in order to avoid this, we are going for the closed loop configuration. In this closed loop system, we can control the operation. We can control the things. So controlling operation is with the help of the closed loop operation. Here there is a connection between output side to the input side. That is with the help of the resistance. With the help of the resistance or the capacitance, we are calling this as feedback resistance, RF. RF is nothing but the feedback resistance. The feedback operation is controlled by this resistor. Hence the name called as the feedback resistor. Here, if you want to increase the gain, we are going to alter the value of the RF. In order to change the output value or controlling operation, we are going to control with the help of the RF, the feedback resistance. This feedback resistance value we are going to alter so that it will increase or decrease the gain of the system or the op-amp. That is why we are going for the closed loop system. Hence we are concentrating on the closed loop operation for the real life systems. Okay. The next topic is application of the op-amps. First one, we are considering the application as inverting op-amp. Let us consider the circuit. This is a circuit diagram of an inverting amplifier, inverting op-amp. Here the name indicates that it is inverting. We are applying the input voltage at the inverting terminal and non-inverting terminal is grounded. So I will call this as terminal A. This is the node A or terminal A. This is the terminal A. And this is the output voltage because which is at the output terminal. The non-inverting terminal is connected to a ground, it is grounded, and we are applying the input voltage through the resistance R1 to the inverting terminal. With the help of the feedback resistor, we are connected between output side to the input side. We are calling this as feedback resistor for controlling operation. This is nothing but the closed loop circuit. Okay. Now, you studied that in the last topic, the virtual ground property. Whatever the potential at this terminal is same as the potential at this terminal by using the virtual ground property. Therefore, we can say that the potential at point A is equal to 0. And due to this, the current I is flowing in this direction. The same current is flowing in this direction I. I is the current which is flowing through the circuit. Vin is the input voltage we are applying. So let us consider that the input voltage, which is sinusoidal wave, we are considering with respect to time. This is V input 0, pi, 2 pi. The output voltage VO, which is 180 degree out of phase with respect to input voltage. Observe here, this is the positive going cycle, this is negative going cycle. That means the output voltage and input voltage are 180 degree out of phase. Hence the name called as the inverting op-amp. Let us go for an derivation of the inverting op-amp. Let us consider that the current I flowing through R1, same current flowing through the RF. So here I am considering the expression for the current I. The current I is given by, from the circuit, I equal to the potential difference between these 2 points divided by the resistance. That is, I is equal to, the potential difference in this point is Vin and this is VA, Vin minus VA dividing by the R1. That is Vin minus VA dividing by R1. Therefore, what is the value of VA? VA is 0. That is substituting for VA as 0 value. Therefore, the current I is equal to Vin minus 0 dividing by R1. That is equal to I is equal to Vin by R1. I will call this as expression number 1. Similarly, the current I is also flows through the RF. Therefore, the current direction is from A to output side. Therefore, we can write the expression for I is VA minus VO dividing by RF. So, I can write I from the current through RF, I is given by VA minus VO by RF. Okay. What is VA value? We know that by using virtual ground property it is 0. So therefore, I can substitute this as 0 minus VO by RF. Therefore, I is equal to minus VO dividing by the RF. So call this as expression number 2. Comparing expression 1 and 2, LHS are same. I. That means LHS are same means RHS is also same. By using that property from 2 and 3, from expression 2 and 3, we can write, so minus VO by RF equal to Vin by R1. Rearranging the terms, VO is equal to minus, I will take this side, minus RF cross multiplication RF by R1 into V input. So this is nothing but the expression for the inverting amplifier. Observe here, this RF by R1, that is nothing but amplification factor again of the inverting amplifier. So this is nothing but amplification factor of the inverting amplifier, that is RF by R1. And one more thing is, this is minus. Minus indicates that output and inputs are 180 degree inverted, 180 degree out of phase. That's what here. This is input and this is output. So that is, so input and outputs, this is the output, this is the input, those two are 180 degree out of phase. This is the input and this is the output. So those two are inverted with respect to input and output. This is nothing but inverting op-amps. The next one is non-inverting op-amp. The next one is non-inverting op-amp. Similar to inverting op-amp, here also we are using op-amp. Here the closed loop with the help of the feedback resistor RF, and the resistance R1, so which is used as input resistance. Here two terminals, non-inverting and inverting. The inverting terminal is connected to ground and we are applying the input voltage Vin to the non-inverting terminal, that is positive terminal. This is nothing but the output terminal. By using virtual ground property, whatever the potential at this point is same as the potential at this point. That is, the potential at B is equal to the potential at A. Therefore, this is equal to input voltage. Let us consider the derivation of non-inverting op-amp. Here the input is consider a sine wave. The name non-inverting means input and outputs are in same phase. There is no phase shift. Both input and outputs are same phase. That is, the output is also with amplification. That means observe here, this is 1 volt means this is more than 1 volt, 3, 4, 5 depending upon the amplification factor. Let us consider that the current I flows through the RF and R1 are same. So by using the expression for I is given by, through the resistance R1 is given by the potential difference between these 2 points. So the current direction is this side, VA minus this potential is 0 because grounded, 0 by R1. That is, the current I through R1 is VA minus you can call this as the potential C. This is the terminal C. This is VC by R1. VC at this, the voltage at this point is 0. Vc equal to 0 due to common ground potential. So that is Va minus 0 dividing by R1. Therefore, the current I is given by Va by R1. You call this as expression number 1. Okay. Similarly, the current I through RF, feedback resistance RF, is given by the current I. This is the current direction. The potential difference between this point and this point dividing by the resistance. That is VO minus VA dividing by the RF. That is VO minus VA dividing by RF. What's the value of VA? VA is due to virtual ground property. It is a Vin. Therefore, VO minus Vin dividing by RF. Right? VO minus VA is nothing but the Vin dividing by the RF. Therefore, I can write I equal to VO minus Vin dividing by RF. Call this as expression number 2. From 1 and 2, LHS are same means RHS is also same. Therefore, we can write, so VO from 1 and 2, we can write from the expression 1 and 2, we can write VO minus Vin by RF equal to VA, so 1 minute, VA, I am not substituted this, so I will substitute for VA also now only, that is VA is nothing but the Vin. VA is nothing but the Vin because virtual ground property, that is I is also Vin by R1 and this one is VO minus Vin by RF. So by using expression 1 and 2, we can write VO minus Vin dividing by RF, that is equal to Vin by R1. Vin by R1. So just taking Vin term one side and VO term another side, we can write this as VO by RF minus Vin by RF. This minus Vin by RF, I will take this into the right hand side. Therefore, it becomes what happens this one? VO by RF. VO by RF equal to, I will take minus V in by Rf as right hand side, that is V in by R1 plus V in by Rf. V in by Rf. Okay. So take VO by Rf as it is and take V in outside, common factor, that is 1 by Rf plus 1 by R1 or 1 by R1 plus 1 by Rf. So go for cross multiplying this with respect to Rf. So I can keep VO as it is. VO equal to V in into Rf by Rf. This is Rf by Rf plus Rf by R1. So Rf by Rf is 1. So VO equal to 1 plus Rf by R1 into V input voltage. This is nothing but the expression for an non-inverting amplifier. The output voltage and the input voltage are in same phase, positive only, same phase. And 1 plus Rf by R1, this term is nothing but amplification factor of non-inverting amplifier. That is, input and outputs are in same phase with some amplification factor.